And welcome to a very special evening, specifically for the Department of Chemistry. I think it is indeed special to welcome two new professors in chemistry in the year of the periodic table, declared by United Nations. So we're celebrating 150 years of the periodic table this year. And therefore, indeed, the special occasion also to welcome two new professors in chemistry. Professor Mallon, the executive head of the department, has also reminded me that we've never had an event to celebrate the new facility that we have for first year chemistry students. So in a way, I think this is also an opportunity to congratulate the department with their new facilities. I would specifically like to welcome the Vice Rector, Professor Nico Koopman. He's the Vice Rector of Social Impact Transformation and Personnel this evening. Our two Vice Deans, Professor Ingrid Lewitsky and Professor Willem Visser, and the head of the department, Professor Peter Mallon. And then, of course, our two honorary guests, not that they're guests tonight, Professor Catherine Esterhuizen and Professor André Villiers. A special word of welcome also to their loved ones and friends in the audience, specifically Professor de Villiers' wife, Teresa, his sister Anne and her husband, Reinhard Folly, his sister-in-law, Marilee de Villiers, and unfortunately his parents and his two brothers can't be here tonight, but I'm sure they will be able to watch the video afterwards. And then also a warm welcome to Professor Esterhuizen's husband, Matthias, and two children, Freer and Sebastian, her parents, April and John Thompson, and her mother-in-law, Jutta Esterhuizen. And then also a warm welcome to colleagues and friends. I also see colleagues here from our neighboring universities. So warm welcome and thank you for celebrating this very special event with us this evening. So I would just like to explain the procedure. So I will introduce first Professor de Villiers, and then he will present his lecture. Then I will introduce Professor Esterhuizen. She will give her lecture. And then Professor Peter Mallon will do the thank yous at the end. So, Professor André de Villiers was born in the Western Cape, but completed high school in the North. But fortunately for us, he came back to the Western Cape and enrolled as a BSc student at Stellenbosch University in 1995. He graduated in 1997 and received the Merck Prize for the best final year chemistry student in that year. This was followed by a BSc honors degree as well as a master's degree, and finally he obtained his PhD in 2004 under the supervision of the well-known Professor Pat Sandra. This was followed by a postdoctoral fellowship at the Pfizer Analytical Research Center at Ghent University in Belgium from 2004 until 2006. He was appointed as a lecturer at Stellenbosch University in 2006, and since then he has built a strong research team. Many PhD and master students have successfully completed their studies in this dynamic group. And the group specializes in fundamental studies as well as practical applications of advanced separation techniques such as multi-dimensional liquid and gas chromatography combined with mass spectrometry. André has published an impressive number of excellent research papers and a book chapter that has been cited more than 2,500 times. He has received several international and local awards, and I'm not going to mention all of them, but just recently in 2015 he was awarded the very prestigious South African Chemical Institute's Great Medal. He was also listed as one of the top 40 under 40 analytical scientists worldwide by the Analytical Scientist. He has not only been successful in obtaining research funding for his own group from various sources, but he has also played a major role in getting funding to expand the analytical equipment in the department. He's often invited as a plenary or a keynote speaker at international and local symposia and conferences, and has served on the organizing committees of many of these conferences. André currently chairs the Western Cape Board of the South African Chromatographic Society and is an editorial board member of 3 internationally recognized journals. And then he still finds time for hobbies as well. So he loves to play soccer, he surfs, and he also hikes. So with this brief introduction, this is now my privilege to invite André to give the address with the title New Dimensions in Chromatographic Separations. Thank you.
I'll do this in my hand. Good evening, everyone. Thank you for coming. I'm going to darken the room a bit just so you can see the slides a bit better. And then I'm going to try and get my pointer working. Okay. So as I said, thank you very much, Professor Barnick. Thank you for everyone who came tonight. I must admit that giving a lecture like this is a bit of an intimidating experience, because essentially what I'm going to have to try and do in the next 30 minutes is explain to you what I've been doing with most of my life for the last 20 odd years or so. And this is a question that as academics we very often get asked, and this always makes me think of a quote that I read many years ago that I managed to find on the internet. And to date I still haven't found a 30-second answer or a suitable answer to this question. So what I'm going to try to do today is give you the 30-minute answer to this question, what it is that I do exactly. And I thought I'd start off, as so many things in life do, in my opinion, with a glass of wine. I hope that most of you in the audience are quite familiar with this sample, and I'm going to use this to illustrate the type of research that we do. So for the introduction, I'm going to focus particularly on one aspect of wine, the wine aroma. Now this wine aroma is a very complex phenomenon. It's complex from a biological perspective regarding the receptors in your nose and the signals they send to your brains, but what I would like to talk about is the chemistry responsible for wine aroma. What are the molecules that determine the wine or the aroma of a particular wine? Well, these are generally a series of organic molecules, relatively small, they're relatively volatile, so you can inhale them into your nose. And these vary between things like alcohols and esters that are formed during fermentation. We also get grape-derived products, and some products like vanillin that you see on the top there, which are essentially enter the wine during wood aging. But to study the chemistry of wine aroma is challenging for two main reasons. One of these has to do with the complexity of the matrix. So, for example, more than 800 volatiles have been identified in wine today. So, this makes the study of their chemistry very challenging. And there's a second aspect, which I use three examples for here. One of them is isoamyl acetate. That's a compound when you open a relatively young pinotage. Often this is what is responsible for that banana aroma. The second one is eugenol, which contributes a nice clove-like aroma, and the third one might be well known as isobutyl methoxypyrazine. That compound is responsible for the green pepper aroma of Sauvignon Blanc and some Cabernet Sauvignon wines. And why I chose these three examples is because they occur naturally in wine at vastly different concentrations. So I realize this is not really a chemistry audience, so to give you an idea, imagine you take fine salt, and you take about 6 grains of this fine salt, and you dissolve it in 1 liter of water. That will give you a milligram per liter. If you take the same 6 grains and dissolve it in the backyard swimming pool, that would be about a microgram per liter. And take the same 6 and dissolve them in an Olympic-sized swimming pool, and that will give you roughly a nanogram per liter. And it is true that very often the most important aroma contributors are the trace level compounds such as methoxypyrazine, and also the one that you see on the left there, which is the compound responsible for the Shiraz pepper aroma. So what we have to do to study the chemistry of wine aroma is essentially we have to deal with this very complex matrix and also the very vast differences in concentrations for these molecules. So with that, what is it that I do exactly? Well, I'm an analytical chemist, and what we try to do is determine the chemical composition of matter. This is important because the chemical composition of any form of matter determines that matter's properties. So there's two main questions that we're trying to answer. What is in a sample, and how much of these constituents are present in the sample? And importantly, in the case of complex mixtures such as wine, before we can obtain this chemical information, we need to separate these compounds because of the complexity of the sample. And that's what I typically do. So I'm a chromatographer by training, so we use a technique called chromatography to separate these molecules. And so I'll start off by explaining in basic terms what chromatography is. There's two main forms. The first is called gas chromatography. We use in gas chromatography very long and very narrow columns to separate molecules, and these columns are coated on the inside, a little white line, by a thin layer of a liquid stationary phase. We then use a constant flow of inert gas, such as helium or hydrogen, to transfer the analytes through this column. That's where the term gas chromatography comes from, but this implies, of course, that GC is used mainly for the separation of volatile and semi-volatile components. For non-volatiles, we work with liquid chromatography. Here the columns are broader, they're shorter, and we typically pack these columns with very fine particles. The mobile phase that we use here is a liquid, so typically methanol and water combinations or acetonitrile. But because we're trying to force a liquid mobile phase through a column that's packed with very small particles, of course we require high pressures to do this. And typically nowadays we work at pressures up to about 1,000 bar or atmospheres. And this means that this column is typically enclosed in stainless steel, and it's very short to limit the overall pressure of such a separation. So those are the two columns that we use to separate molecules in liquid and gas chromatography. But how do we do this experiment? Well, essentially we place a detector at the outlet of the column, and then we're going to inject a mixture of molecules at the inlet of both columns. And what will happen now is that the mobile phase, the gas or the liquid, will transfer the analytes to the outlet of the column. While this happens, the analytes are going to interact with the stationary phase, and in the case of liquid chromatography, also with the mobile phase. And this will affect the time they spend in the column, and based on this, we can separate them. So to illustrate, this is a mixture of 3 compounds that we separate using gas and liquid chromatography. And what we obtain at the end of this experiment is, well, 2 chromatograms, which is essentially a picture of the separation we just achieved. That's basically a plot of detector signals as a function of time. So we can see that in each case here we separated 3 different compounds. The retention times we can use to identify the compounds, and the areas underneath these peaks correspond to the number of molecules that we injected, so we can quantify them also. For highly complex samples though, identification by retention time is not very reliable. So what we use for that is a technique called mass spectrometry. So there's a basic schematic of such a system. What we do in mass spectrometry is essentially a neutral molecule enters and we ionize this. In this case, we remove a proton and we generate a negatively charged anion, which is transferred then to a high vacuum region of the mass spectrometer. And what's going to happen here is that there's a little electric pulse at the inlet which sends that ion towards the detector at the outlet. And the time that this takes is related to the mass and the charge of the ion. So a mass spectrum is then a plot of the intensity of ions as a function of mass to charge ratio. And this we can use to identify compounds. So how we would do this in liquid chromatography mass spec, we separate the molecules, but the mass spectrometer now acquires online mass spectrometric data as the compounds elute from the column. And therefore, we can afterwards access the mass spectrum of a compound and use this to identify it. In this case, we have accurate mass data, so we can determine the molecular formula of the compound and use the fragmentation information to identify it. And so, GC and LCMS are very extensively used in industry and research because of the excellent performance they offer. So I showed 2 examples here. That's the analysis of honeybush volatiles by GCMS. And you can see that we can separate a large number of molecules in half an hour or 40 minutes. Same is true for LCMS. So this is work on proteophenolics. We can separate large numbers of molecules. And of course, using mass spectrometry, we can identify in a single analysis in the order of 100 different molecules. Mass spectrometry can't do everything though, I should point that out. So I use 3 examples here. We have 3 compounds which have exactly the same molecular formula, but they have vastly different aroma attributes. And mass spectrometry can't distinguish between them, so we need to separate them before we can identify them. Now, if this was the whole story, I would actually be an application chemist and I might well be a better surfer than I am today. But of course, like with any technique, there are limitations. Now, in chromatography generally, we use a concept called peak capacity to describe this. It's a very simple concept. Imagine you have a certain amount of time, 30 minutes, and you have a certain average peak width for your compounds that you separate. How many of these peaks can you fit into your 30-minute separation? So that schematic over there is an illustration of a peak capacity of 20. But we can show that when we have highly complex samples where the retention approximates a random distribution, the peak capacity required to separate n compounds should be much larger than n. Okay? And if we consider that GC offers peak capacities of less than 1,000 and LC less than 300 respectively, and we think about the wine sample containing 800 volatiles, the challenge is very clear. We need to improve the separation for highly complex samples. So the problem is illustrated in another way over here. We have a GC column, we separate the mixture of compounds, and what we find is that there's partial co-elution of 2 compounds. One way to overcome this problem is to use a different column, so this contains a different stationary phase, and if we re-inject the same mixture, we expect a different elution order, and that is indeed what we see, but we also see that we have partial co-elution. So of course we can analyze the sample using 5 different columns, but there's a more elegant solution to this, and that is that we take the 2 columns and we combine them in series, and we connect them using a thing called a modulator, which I'll explain how that works shortly, but essentially the modulator is there to take fractions from the first dimension column and transfer them very quickly to the second dimension column, so they're separated over there. What would happen in that scenario is something like this. So the analytes are separated in 2 columns of 2 dimensions, and the benefit of doing this is that now compounds co-eluting in the second dimension are separated in the first, and similarly compounds co-eluting in the first are separated in the second dimension. So in other words, we end up with a 2-dimensional separation space which is defined by the peak capacities in each dimension, and therefore it's intuitive to say that for such a comprehensive 2-dimensional chromatography, the peak capacity is the product of peak capacities in both dimensions. So this therefore offers us a way to get much better performance in chromatography than is the case for conventional one-dimensional techniques. Okay. Now, the last bit of background. When I talk about comprehensive two-dimensional chromatography, we're referring to two-dimensional separations where each part of the sample is subjected to two different separation methods. This is denoted GC times GC or LC times LC, and this is basically what I'm going to be talking about today. There are two important considerations to design an effective comprehensive two-dimensional separation. The first is a fancy term called orthogonality, but it's a very intuitive concept. Imagine we combine two separations which have the same relative retention order. What we expect to see is all the peaks in the two-dimensional space lie on the diagonal, and we have co-evolution for several of these peaks. An orthogonal combination has different retention orders in the two dimensions, and now we're going to have approximately a random distribution, and now we have the benefit that compounds that co-elute in one dimension are separated in the second. So we require orthogonal separations to exploit the benefits of comprehensive two-dimensional chromatography. The second important requirement is a bit more tricky to explain. So this has to do with the time during which the modulator collects fractions from the first dimension and transfers them to the second dimension column. So I'll use a simple example. That's our first dimension column, and we have two partially co-eluting compounds at the outlet of this column. Now, if the modulator were to collect that fraction and send it to the second dimension column, we run the risk that these compounds are not separated. So in other words, what happened here is that we took two partially resolved compounds and we lost this resolution. This is obviously not good, so the way to overcome this is to use shorter fractions. So we sample multiple times across each first dimension peak, and what you can see now is that we maintain the partial separation of the orange and the red compounds. So the requirement is essentially that sampling time should be very short, and when we hyphenate the two columns in series, this means that we have to perform this separation very, very quickly. So I'll explain this when I talk about GC, which is essentially the next part. This is what the instrument looks like, or a schematic of it. So it's quite simple. We have a first dimension column, second dimension column. They hyphenated with what we call the modulator. We have an injector on the first dimension column, detector on the second dimension, and the idea is that a compound is separated in the first column and then quickly transferred and separated in the second dimension column. We need to do this very quickly, so in the second dimension we typically use separation times of 2 to 5 seconds, so very, very fast separation. And in the case of GC-GC, the orthogonality is provided by combining columns with different stationary phases. Now, the essential part of this thing is clearly the modulator, and to illustrate how this works, this is a schematic representation of one such system. We have the first dimension column, the second dimension column, and then we have two hot air jets and two cold jets. These cold jets blow liquid nitrogen, and the idea is that by cooling down the analyte, we can trap it and focus it, and by heating it up, we can release it again because it's a gas phase separation. And so, how this works. A compound elutes from the first dimension column, it's focused by the first cold air jet, and we then switch the two jets, retrap the analyte, and switch them again to transfer it to the second dimension column. At the same time, the next fraction from the first dimension peak is trapped by the first liquid nitrogen jet. And this process is repeated every 2 to 4 seconds throughout the analysis. If you think about this, we have one detector here, so what that detector sees is essentially a series of very fast second dimension chromatograms. So I use real data to illustrate how this works in the next slide. So this is the analysis of a wine sample. The detector signal is as a function of retention time, and what we see is a series of consecutive, very short second dimension analysis. Each of these corresponds to roughly 4 seconds, and ideally we can separate a few compounds in those 4 seconds. But to work with a chromatogram like that's not very easy, so what we tend to do is we chop it up into a matrix and we visualize it in a 3-dimensional format, and often we replot this data in a so-called surface plot and a 2-dimensional contour plot. It's the same data representation of raw GC-GC data. So to illustrate, to finish the example here, I indicate 2 peaks co-eluting in the beginning and 2 peaks co-eluting at the end by those little dots. And we can then find the corresponding peaks in each of the representations that you see at the bottom. So we can see that the yellow and the purple dots co-elute in the first dimension, but they're separated in the second, and the same for the little blue and the red dots. Okay, so that's the background. When I started in Stellenbosch 2006, we didn't have instrumentation like this. So initially we started doing GC research in collaboration with a colleague of mine in Canada, today is Greki. And of course, being in Stellenbosch and having an interest in wine, our first application areas were in the field of wine analysis. So the first student who worked on this was André, and I just show one example here of the analysis of a red wine volatile extract. So essentially the headspace above the red wine. And you can see the complexity of the sample. If you look a bit closer, you can see the number of compounds that we can separate in only part of this chromatogram. And I just indicate the two compounds that I showed previously. That's the second part of the chromatogram that have the same molecular formula but are very nicely separated in the two dimensions. So this was promising, and the next project that we started was done by Jochen Wessner. He's a German national with more of a wine background. So his project focused on studying the effect of malolactic fermentation on wine aroma. So those of you who are not familiar with this, malolactic fermentation is essentially a secondary fermentation where lactic acid bacteria are used to convert malic acid to lactic acid. This de-acidifies the wine, but it also affects the volatile profile, and therefore it affects the aroma in a way which is not entirely understood. So Jochen's work focused on using GC to analyze a control wine with no malolactic fermentation, and then the same wine which was malolactically fermented using 3 different lactic acid bacteria strains. Now this doesn't look very impressive, but if you zoom in a bit, there's a lot of information in such a chromatogram. I illustrate here that we can detect isobutyl methoxypyrazine. You'll remember that's a compound that's present at 1 nanogram per liter level in wine, so it's a very sensitive way of doing things. And taking all of this data and suitable statistical methods I'm not going to talk about, we can differentiate between the control sample and the malolactically fermented wines, primarily in terms of the C6 volatile constituents, which are associated more with a type of cut grass aroma. And we can also distinguish between the wines produced with different malolactic lactic acid bacteria starter cultures in terms of the levels of esters and alcohols and diacetyl, which explains essentially sensory data obtained for the same wines in the chemical origin of these sensory differences. And so more recently, we're working on our GC work focuses on honeybush tea in collaboration with Professor Lisette Bad and Darlene de Beer. I'm assuming that most people are relatively familiar with this also. It's an indigenous herbal tea produced from Cyclopia species. And while honeybush tea is still a relatively small market compared to rooibos tea, there's a concerted effort to increase the market share. One of the things that needs to be done is to evaluate different Cyclopia species and their suitability for the production of honeybush tea. And of course, one of the most important attributes of honeybush tea is its volatile or its aroma. And so we use GC to have a look at this, and you can see if we analyze the headspace of a honeybush tea sample, the complexity of this sample. So we can use then this approach to analyze different species of honeybush tea, and it takes a very long time to go through all that data. But we can identify lots of compounds, many of them new for the first time in these particular samples. And I'll show one example of what we can find. If you zoom in a bit, we find this compound, cinnamaldehyde, present in only the maculata samples. And again, we could then explain the origin of a unique cinnamon aroma of this Cyclopia species, which is not present in the other ones. That's due to cinnamaldehyde. And so up to this point, all of this work was done in collaboration because we didn't have suitable instrumentation ourselves. This has fortunately changed in the last few years, so this is the new toy that we have in the lab. So this is a GC high resolution, high speed time of flight mass spectrometer at the moment. So he's analyzing all wine, Chenin Blancs. And the benefit of what he's doing, or using this instrument, is essentially that now we have accurate mass data. That allows us to determine the molecular formula formula, and therefore identify these compounds with a much greater degree of certainty. Okay, so part 2 of the talk, we'll shift gears a bit and talk about two-dimensional LC. Again, I'll start with the principles. The instrument is relatively basic. We have 2 columns. Each of the columns has a pump to force the mobile phase through. We have an injector in the first dimension and a detector at the outlet of the second dimension. You'll see that modulation is performed in an entirely different manner here. So, looking a bit closer at that, we use a 2-position valve to do this. And how this works is that the effluent from the first dimension column is trapped in the first loop. At the same time, the content of the second loop is analyzed in the second dimension. And when we switch this valve, we will see that the next fraction from the first dimension is now transferred to the second loop. And the content of loop number 1, which was just collected, is analyzed in the second dimension. So if we keep switching this valve every typically 20 to 40 seconds, we can do a comprehensive 2-dimensional liquid chromatography separation. And so we started this work actually before the GCGC work, and what I was very interested in is one particular class of compounds present in wine, so I'll get back to the wine, and that is particularly the wine tannins. So tannins are very important constituents because they contribute to the mouthfeel and the astringency of especially red wines. And this is a consequence of the fact that these molecules precipitate proteins in your saliva, and that's what gives you the mouthfeel and the astringency. Chemically speaking, they're oligomeric phenolics, so we have the 6 building blocks that you see there, 3 pairs of stereoisomers, and they can be linked to form higher oligomers in various ways. So I'll move away from the chemical structures and use very simple dots to illustrate the complexity of these things, because they can form a series of dimeric procyanidins, we call them, and only for the number of dimeric species that's possible is somewhere in the region of probably, I have to go calculate it, but it's probably going to be close to 100 of only dimeric species. And then we get the trimers, which can be formed with different linkages, different units, so the complexity increases exponentially, in fact. So we have an extreme stereochemical diversity and an extreme diversity in terms of the size of these molecules. And this is, in fact, why it's so very hard to study tannins. And so we thought initially, when we started doing 2-dimensional LC, this is a lovely sample to actually explore the potential of the technique. So Martha spent 7 years working on this. I'll show the results in 3 slides. Essentially, the system that we came up with is we use a helix separation in the first dimension and a reverse phase in the second. The terminology is not all that important. But because the mobile phases are not really compatible, we use a split between these 2 dimensions. At least we did in this work. The rest of the configuration is quite basic. We also use a fluorescence detector because these molecules fluoresce. And at the back end of this, we use a mass spectrometry. Okay? And with this, we can then generate this type of data. So that's the raw fluorescence data, raw MS data, which doesn't look very impressive. But if you zoom in, you'll see that each of these peaks is essentially a very fast second dimension separation. And so we can transform this data into contour plot format, and it takes a lot of time to sift through this data and identify the compounds. And here mass spectrometry is very important. So I just showed an example here of the monomeric species, dimeric, trimeric, up to the octamers, where we can see very large molecules up to the degree of polymerization of 16, something that would look like this. Although we don't know what the 3D structure of that is. But the question is this good enough for tannin analysis? And if you look at the mass spectrum obtained in that region of the 2-dimensional plot, the answer is an emphatic no, because this is what it looks like, and we can distinguish 2 series of co-eluting high molecular weight compounds that co-elute after a 2-dimensional separation. So clearly, this is going to keep us busy for a number of years still. There's another class of compounds in wine that we also started to investigate with 2D-LC, and this is the anthocyanins. These are the compounds that give us the red color of red wine. So they're present in the skins of the grape, and when you extract them during winemaking, a young wine is often very dark red and purple because of the high levels of these molecules. But while the wine ages, these anthocyanins are involved in a series of interactions, and they form a whole series of derived products with different color properties, and this is what's responsible for the change in color of a wine as it ages. This is a bit of a simplification though, because we have about 15 of those and 15 of each of these, and we have a number of additional reactions. But one of the ones we're interested in particularly is the addition of tannins to the anthocyanin structure. So we have this complex family of tannins, the complex family of anthocyanins, and they form derived products. And so clearly, we have no idea how many of these things there are, and we used two-dimensional LC to have a look at this. This is the work from André's PhD. So we use a similar configuration to Martha's work, but I should say when I show these schematic illustrations, that all looks very simple, but to do an experiment like this, essentially, everyone in the lab is forced to get a trolley and carry our instruments, literally across Merriman to Mariki's laboratory, and when we get there, we tend to take over the place for a bit. So this is what the instrument actually looks like. So we have a LC here and LC at the back. There's the mass spectrometer, and that's the valve that is used to to modulate for the 2D LC separation. With this system, we can get very nice pictures of very nice separations. This is a 6-year-old red wine, so there's relatively low levels of anthocyanins, but you can see the complexity of the sample. And of course, using mass spectrometry, we can then start comparing profiles of wines which were produced in the same manner on the same farm, but differing in age, and we can then start to study the evolution of pigments as a function of time. So we can see the grape-derived anthocyanins disappear, the tannin adducts start to appear, and we also have a whole series of derived products that I won't talk about that appear, and we can therefore study when these compounds start contributing to the color of aged red wine. And so, that's to give you an idea of our 2D LC research. What we are doing at the moment is we're focusing a bit more on an aspect which is challenging because the technique itself is relatively complex, but method development in 2D LC is particularly complex. And so this is a bit of a self-indulgent slide. There's a lot of equations here. I'm not going to talk about them. I'm using them to illustrate one concept. And that is, what are we trying to do in method optimization? We're trying to maximize the peak capacity, minimize analyte dilution, and do this as fast as possible. The problem, of course, is that these are mutually exclusive goals. So generally, if you want maximum peak capacity, you have to sacrifice dilution or time. So how would you go about this? Well, we're combining two one-dimensional separations, and each of these has its own set of parameters which we can optimize in the conventional manner. That's relatively easy. The problem is that in 2D LC, we add a modulation step with an additional series of parameters, and if you look at the relationship between all of these, the problem becomes clear. So this is what we're working on at the moment. Margriet Miller's PhD and master study is developing a software program that will allow us to optimize LC-LC separations in an automated manner. So how she does this, I don't understand all of it, but essentially we use input parameters such as analyte properties in the columns. We use well-known chromatographic theory, and that gives us all possible combinations of experimental configurations. We then remove those that are not practically feasible, and the remaining ones we optimize using multi-parameter or Pareto optimization. What the output from this looks like is something like this. So we have an analysis time, peak capacity, dilution, and these are the Pareto fronts. They correspond to the optimal conditions of that combination of analytes and columns, etc. So any point on the inside provides suboptimal performance, any point on the outside is not obtainable, and every point on these Pareto fronts corresponds to one optimal configuration, and we can get all the experimental details from that, and then you go to your instrument. And we've been using this quite a lot in the last few years. I'll just show you a few examples. That's the analysis of grapeseed tannins, and that's the analysis of the non-colored phenolics in wine. And I'm not sure how I'm doing for time. I'm probably over time, I apologize. But I would like to spend the last 5 minutes, again, shifting gear a bit and just talking about where we are at the moment and where we think we should be going. And to do this, I used two examples. Again, the volatile analysis of volatiles in wine, and the analysis of pigments in red wine. This is the first paper reporting the analysis of pigments in 1978, and you can see pretty good performance. Same for the GC separation on top, considering that this was a number of years ago. But if you look a bit closer at these chromatograms, you will see there's many instances of co-elution. And so if you fast forward about 30 years, we can use capillary gas chromatography and what we call ultra-high pressure liquid chromatography, and we get much better separations than was possible in the 1980s. But again, if you look a bit closer, you'll see instances of co-elution. And so, of course, we can use comprehensive two-dimensional chromatography, and we get much more detailed information about both of these fractions. But rather depressingly, if you go dig a bit closer, you're going to see many instances of co-elution. So what I'm trying to illustrate here is that we're not essentially there yet. We're trying to separate very complex mixtures, and for this we know that the peak capacity we require should be much larger than the number of components we're trying to separate. We know that 1D GC and HPLC do not offer this performance at the moment, and we know that we can do much better using comprehensive two-dimensional GC and LC. So if you look at this, the next obvious question is, why don't we do three-dimensional chromatography? Well, it has been done, but it turns out if you combine 3 columns in series, the performance gain is not very significant, the reason being due to these sampling constraints. So what people are looking at now is essentially combining time and space-based separations, and this theoretically should give us a very high peak capacity, but this is very far from being implemented. So what we're trying to do is focus on something different. We're trying to exploit the advances in advanced mass spectrometry. So one topic that we're pretty interested in at the moment is a thing called ion mobility mass spectrometry, and what this is, so you'll recognize this, that's a time of flight mass spectrometer, that's where we ionize molecules, but we add an additional cell there. That's an ion mobility cell, and that cell is filled with buffer gas, so typically nitrogen. We apply a potential difference, and the ions are accelerated across this. As they move across the cell, they collide with the nitrogen, and therefore we can separate these ions based on their charge and their size. Okay? And this can be done very quickly, it can be done in the millisecond time scale, and so ideally, this is compatible with chromatographic separation, because in LC we separate on the minute time scale, in ion mobility milliseconds, and the time of flight separates ions on the microsecond time scale. And the big benefit of doing this is that we have an additional separation step. So for example, if we have compounds co-eluting in chromatography, provided that they have different drift times, we can identify compounds that have even similar mass spectral behavior. And so, if you think about this and you think about everything else that I talked about, of course we were going to ask ourselves, why don't we combine this with two-dimensional chromatography and get a three-dimensional separation? And we recently did that, so combining two-dimensional LC with ion mobility and mass spectrometry. And the type of data that we get is shown here for grape seed, so it's a three-dimensional separation, where that's my helix separation, that's the reverse phase separation in half a minute, and that's the ion mobility separation in millisecond time scale, so 7 milliseconds. And again, there's a lot of information in these plots. I'll just show one benefit of this. Looking at the trimeric procyanidin molecules, that's the contour plot that we obtained, so we can see 4 compounds nicely separated. But if you look at the ion mobility trace, you see 2 arrival time distributions. So this means there's 2 species that we can't separate by two-dimensional LC, we can't distinguish them by mass spec, but we can get additional information about them using ion mobility. And so we think that this technique shows some promise in our work going forward, especially on wine tannins. And so that brings me then finally to a summary. Separations play a very important role in a lot of fields of research and also in industry, because these industries and fields of research deal with complex mixtures. We know that conventional 1D GCMS and LCMS offer excellent performance, and indeed they're used very extensively globally to separate complex mixtures. But we also know from the theory of chromatography this is not always enough. So we can do much better using comprehensive two-dimensional GC or LC, but there's still some work to be done, which will probably keep me busy until I retire in about 2 or 3 years. And with that, then I'd like to thank many people, my family, my wife, my friends for their support. Special word of thanks to my parents, who unfortunately couldn't be here due to my poor admin skills. A lot of all the postgrad students who did all of the work that I'm talking about here, and has made this quite a enjoyable experience for the last 30 years. My mentor, Pat Sandra, without whom none of this would have been possible. A series of collaborators, locally and internationally. I'd like to highlight 3 people here, Frederick Lennon, Therese Gurecki, and Mariki Stander, that I've been working with for many, many years. And then my colleagues and students in the department, and financial support from SASO, particularly NRF Financial and Technologies. And I'll leave you with 2 thoughts then. One is taken from a Winnie the Pooh book because I thought it was rather apt. It's apt on the one hand because this was much harder than I thought it would be, and on the second hand because it's certainly time to stop now. But to balance the Winnie the Pooh quote, I thought I would use one from my favorite Nobel laureate about research. So for those of you who are interested in reading up on this, there's a little booklet that you can consult. Robert Zimmerman might be better known to some of you as Bob Dylan, by the way. So he's not a chemist, but you should know what he's talking about. And with that, I'd like to thank you all for coming, and thank you for listening to me. Thanks.
Now, we are very lucky to have 2 outstanding academics, and I will say a word or 2 first of all about André de Villiers. As you've seen, André's research is really at the forefront of pushing the boundaries of what is actually possible with chromatographic fractionations. And it's really amazing to see what is actually possible in terms of separating and identifying the different compounds. Those of you who know André know that he is an absolutely passionate researcher. André is the happiest when he's in his lab, working with his students, doing his thing, and certainly that is something I think that you saw coming out in his lecture this evening. Chromatography and fractionation at Stellenbosch has a very long and proud history, pioneered by several people, including Ben Berger, who I see is in the audience. Pat Sandra made contributions, and I think we as a department are extremely happy to say that the chromatographic side of the research in our department is in very, very good hands. I think we can confidently say under André's continued contributions that Stellenbosch University, and specifically chemistry at Stellenbosch University, will continue being a place in the world which is seen as doing cutting-edge research in the development of chromatographic techniques. I have to say a word about André as well. He's probably one of the nicest colleagues you could possibly ever have. André is one of those people that really does chip in. He's I won't say he's always willing to help, but that's not strictly true. André will say no, 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 and you've got to keep going and say, no, André, we need you to do this. Eventually, André does agree to do it. And the reason, of course, we asked him to do it because we know that when he does agree to do it, he does an absolutely outstanding job. So he's really a fantastic colleague to have. And I'm afraid I'm going to have to say a word about André. I like to tease people and joke. And André is really the colleague that is the target of a lot of the teasing and joking in the department. It started many years ago, actually. When I started at Stellenbosch, I was teaching a third-year course, and André was simultaneously teaching a third-year analytical course. In those years, the 2 courses ran concurrently, and the students one day in the prac were talking about, analytical chemistry. And I said, who's the lecturer? They said, no, that guy. So I said, but what guy? And one of the students said, no, that dude guy with the ponytail. And I thought that was quite funny. I think after that we had a program committee meeting, and I said to André, the students call you Dude. And I said, well, from now on I think we should call you Dr. Dude. And like most nicknames, André was, absolutely don't call me Dr. Dude. And unfortunately, of course, as soon as you do that, that nickname sticks. So Dr. Dude was a member of our department. It became Prof. Dude. In fact, he's Professor Dude. The Dean mentioned André is a surfer. He's a surfer dude, and one of the interesting things I said to André, or André actually said to me, he thinks he's actually a better surfer than he is a researcher. I've never seen him surf, but that would take quite a lot, I would suggest, to be a better surfer than a researcher. I'll give one anecdotal story about André as well. One of my most memorable moments as head of department, André comes into my office one morning. He clearly just smoked a cigarette. He had his triple shot of espresso. You know, André is definitely stressed. And he said, Peter, you won't believe what happened. I said, André, what's the problem? No, he said, I can't believe it. You won't believe what happened. So I said, André, what is the problem? And he said to me, no, he had a lecture, and his alarm clock didn't go off, and he missed the lecture, and this is an absolute disaster. Now, of course, I couldn't resist because of his reaction. I said, André, this is absolutely the worst possible thing that could happen. And André, I know, I can't believe this happened. I said, André, I don't know what we're going to do. I'm going to have to phone his in. But as I say, André is always a good sport and somebody we like, or certainly it's a good sport taking part in these things in the department. So that's more or less it for the evening. We are in the first year lecture facilities, and this complex has lecture halls plus the undergraduate laboratories. I'm pleased to say that we have an assignment and a practical for you after this. You've heard and had a discussion with regards to wine and the various components. There's about 800 volatile compounds in a pinotage. The task for you now is to go downstairs and try and identify and see whether you can identify some of the 800 different compounds. So please join us downstairs.